Hi and welcome to the multi-agent learning course. Today we're going to discuss the replicator dynamic in more depth. And prior to discussing the replicator dynamic, we will discuss symmetric games and symmetric Nash equilibria in symmetric games, asymmetric Nash equilibria in symmetric games, because I want to emphasize that in symmetric games, which are important for Nash equilibria, asymmetric equilibria exist. Then we'll move on to evolutionary game theory and discuss important concepts there. And then we move on to the replicator dynamic itself. Discuss the concept of fitness vector and score matrix, which is the ground table. If the species of the replicator dynamics are reply rules, then we talk about the ground table rather than of a score matrix. And we discuss the continuous replicator equation, which is the most famous instantiation of the replicator equation. We discussed the discrete replicator equation, that is the replicator equation which you are going to work with in the programming assignment, because computers are only able to deal with discrete entities by nature. And the discrete replicator equation and the continuous replicator equation, for that matter, are not defined in and of themselves, but follow from the discrete step equation. So I will refer to a derivation of the discrete replicator equation from the discrete step equation, but I will not discuss it at length, because you can peruse the slides yourself, and we'll see to what detail we discuss those derivations, because they are not of immediate importance to the practical assignment. And the continuous replicator equation can derive on its turn from the discrete replicator equation. We'll discuss properties of the replicator dynamic and the connection of the replicator dynamic with Nash equilibria. So first, we already know and have familiarity with symmetric games, but to be more precise, I want to discuss ways to denote symmetric games. So in a symmetric game, only your actions do matter and not your role. So it's not important if you are, in a two-player game, if you are a row player or a column player. It's just only the actions that you execute do matter, whether you are a row player or a column player. So on the left-hand side we have a symmetric game in its full representation, which is the payoffs of the column player and the row player. But you see, part of the matrix is redundant, so we can just as well leave it out, because the payoffs, because of the game is symmetric, the payoffs of the row and the column players are swapped here. So this information in the lower left section of the matrix is redundant, so we may just as well leave that out. So that was on the left is the bimatrix representation, and instead of this representation here as a partially filled bimatrix, we may represent a symmetric game as a plain matrix, like so. And these payoffs indicate what the row player receives if it encounters the column player. So for example here, if the row player plays a second action and the column player plays the first action, then the row player will receive 3 utils. So an very important example of a symmetric normal form game is Hawk-Dove game. The Hag-Dove game is occurs in many scholarly publication on game theory because, well, it has all kinds of social applications. So the scenario is there are two parties and both can assume the stance or the attitude of a hawk, either a hawk or a dove. And the hawk is the aggressive stance. So, for example, the two parties are Russia and the United States, or in a political context. Or so one is the aggressor, or one stance is the aggressive stance, the hawk, and the other stance is the peaceful stance, or the passive. Well, the peaceful stance, being the dove. And the idea is that the two parties compete for a resource V, a value V. And well, if both parties are peaceful, they just share the resource. However, if one party is aggressive and the other is not, then the aggressive party takes the full resource, seizes the full resource, seizes on the full resource. And if the row player is a passive party, the column player takes the whole resource, so the row player gets nothing. If both parties are aggressive, then they share the resource, but also share the possible costs that involves, or that is the result of fighting. Fighting incurs damage, and damage implies cost. So we have to subtract the cost from the shared profit. So that's the Hag-Dove game. Well, if you instantiate it, you will get here the what is it? The chicken game. So with this particular instantiation and other instantiations yield analog versions of the prisoner dilemma or matching pennies or stack hunt. So the Hag-Dove game is quite versatile scheme. So this game is a symmetric game, and the game is symmetric when players have equal actions and payoff. So for one player, if he plays a certain action in the in a particular coordinate, then that's the same as the other player plays that action in the opposite coordinate, and the same action as the opposite coordinate of the original player. May sound a bit confusing, but it's just that, well, this just indicates that you can swap here the payoffs, like so. And here, of course, you swap on the main diagonal, so these should be these two should be equal. And an equivalent definition of a symmetric game in a two-player case, that's more intuitive, or it is more comprehensible, is that the actions of the row player, the number of actions of the row player equals the number of actions of the column player, and the payoff matrix of the column player is the transpose of the matrix of the row player. Well, you see that here. The matrices are transposed. So, if you have a strategy of an n-player symmetric game, so a symmetric game in which n, lowercase n, players participate, then if P is a strategy, so a probability distribution among a finite number of actions, then the n vector, because you have n players, is a Nash equilibrium. Well, if the n vector is a Nash equilibrium, then we talk about a symmetric equilibrium. So a symmetric equilibrium is an equilibrium in which all parties maintain the same strategy. So it's very important to realize that if you know a symmetric equilibrium, then you know the strategies of all players. And if you know the strategies, conversely, if you know the strategies of all players, then, and you know that you're dealing with a symmetric equilibrium, then this is enough information to constitute the symmetric equilibrium. So one strategy is sufficient, of course, to know the entire symmetric equilibrium. Now, from John Nash, we know that every game in normal form has a Nash equilibrium, but it's also a theorem that every symmetric game has at least one symmetric equilibrium. However, symmetric games can have asymmetric equilibria. This is very important for your programming exercise. You may not expect, but it is important, because you have to compute the Nash equilibria of the ground table, and those set of Nash equilibria can have asymmetric can have asymmetric equilibria. So how are you going to interpret those asymmetric equilibria? That's up to you, and I'm very interested in how you interpret those asymmetric Nash equilibria of the ground table in your study document. To give an example of a symmetric game that has asymmetric equilibria, well, there's one symmetric equilibrium, that is if both players threaten each other 1/3 of the time. That's the symmetric equilibrium. That's an unstable equilibrium. You know by now of the gradient descent course, the course on gradient dynamics, or the lecture on gradient dynamics. But these are the two asymmetric Nash equilibria. These are pure equilibria, so it's very easy to see that these are Nash equilibria. And of course, it's also very easy to see that those two are asymmetric equilibria. So now I'll move on to evolutionary game theory. So the idea of evolutionary game theory, I already explained it in the slides on the bachelor programming assignment, is that you have a finite number of species. Here we have 1, 2, 3, 4, 5, 6, 7, 6 species, and of each species there are infinitesimally many individuals, and each of these individuals has a probability to compete against one of the others. So if we focus on the species of the blue type, well, the probability that one individual of a species of the blue type competes against a species of the yellow type is a bit smaller than that it would compete against species of the brown type. But that's the idea. And according to the success of the species, the proportion of those species will grow or shrink. So if yellow is quite successful against blue, pink, purple, orange, brown, and so on, then the proportion of yellow will grow at the cost of the proportion of the competing species. So as an example, you say you have 5 species, and an encounter between individual different species yields payoff for both. Now, as an example, for example, an encounter of an individual species 1, species 2 against an individual species 1 yields -1 for species 2, -1. So the numbers always indicate what's in it for a row. Now the idea is that the population consists of a very large number of individuals, each playing a pure strategy. And individuals, that's very important. The interaction is homogeneous. That means location and time is not important in the probability of interacting with an individual of some other species. Only the proportion of all other species is important. So there are other models, for example with cellular automata, but their location is important. But here location is not important. We are only interested in the proportions of the species, which must add up to 1. And you can calculate the fitness of the species if you know the proportions of the species. For example, well, it must add up to 1. So this is 0.1, 0.2, 0.3. We are at 0.5, and then 0.2. S4 is 0.2 and S5 is 0.3. Hopefully this adds up to 1. So if an individual of species 1 competes with the population, then it has an 0.1 probability that it will score a 6. And an 0.2, well, what did I say? 0.3. 0.3 probability that it will encounter a species of type 2, and then it will score a 7. And it will have a probability of 0.1 that it will encounter a species of type 3, and then it will score a utility of O. So the score or the fitness of an individual species I is, well, just sum up this row, well, for species 1, weight by the proportions, weighted by the proportions, of course, because if a proportion is very much present, the score, for example, is the second type is very much present, then this score should weigh much more. You should be accustomed with this notation. It takes some time to understand, but just write the matrices out, and this is well, this equation is equivalent to multiplying the entire matrix with the proportion vector and then taking the ith component. So multiply the matrix A with the proportion vector, and you will get a vector of length 5. And if you're interested in the, well, you take the first. And the average fitness is, well, the fitness of all weighed by their proportions. So this is basically multiplying the ground table or the score matrix A with the proportion vector, and then you have a vector here, and then you compute the in product of the same vector, but then the flat vector, the horizontal vector, the transposed vector, with the result vector here, and you get a scalar, and that's the average fitness. The average fitness is just a weighted average fitness. So now on to the replicator equation. The replicator equation was first discussed by Taylor and Jonken only in 1978, and got its name by Schuster and Sigmund in 1983. And this is the quote where it first appeared, just for the sake of history. And it's the most important game dynamics studied in the connection with evolutionary game theory. And evolutionary game theory, on its turn, is proposed and developed by Maynard Smith and Price. So, just for historic sake. So, Schuster and Sigmund observed that several evolutionary models in distinct biological fields, such as population genetics, population ecology, early biochemical evolution, and sociobiology, lead independently to the same class of replicated dynamic. Well, we can now add one more field of application, the comparison of multi-agent learning algorithms. So there's the replicator dynamics pops up at different fields. Recently I got a mail from a master's student who is working on its thesis, on his master thesis, who discovered that in some other field, cell metabolism, which works as a metaphor for computational process, which details I don't know, also was naturally leading to the replicated dynamic. So the replicated dynamic, well, the bottom line of this quote is that the replicated dynamic is omnipresent. 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 Is everywhere. So the replicated equation models how n different species grow or decline due to mutual interaction. It is assumed that if an individual species I interacts with an individual species G, the expected reward for the individual of type I, so the role player, is constant. So for the programming assignment you have to compute the ground table. What this means for the program assignment, you have to compute this number once. Only once. Maybe even out the variation by restarting episodes more than once, and then even out, so take the average. But this is then your constant score of reply rule I against reply rule G, for example, if I is fictitious play and G is no regret. Well, then these constants are summarized in the relative score matrix or ground table if you're working with reply rules, and the number of proportions of species I is denoted, or the number of individuals of species I is denoted by Q. At time t, or at round t. T can be discrete or continuous. So if it is discrete, you speak of rounds. And then, well, you're not really interested in the number of individuals. You abstract from that, and you are interested in the proportions of species I. And, well, this is just the QI normalized. So the PI are proportionally related to the QI in such a manner that they add up to 1. So the fitness, we already discussed the fitness in the concept of evolutionary game theory. It is an expected reward when it encounters a random individual in the population. Expected because it encounters according to the proportions, but it randomly selects an individual. Now, as an example, suppose we have here a score matrix and here a proportion vector. So the proportion, of course, must add up to 1. So species 1 takes 10% of the proportion, species 2 takes 40%, and so on. Then the fitness vector, which is A times P, can be computed just by matrix and vector multiplication. So the first element of the result vector is the first row, the first row times this vector here, and the second element is the second row of the vector, the second row of the matrix times the vector, and so on. The third component of the result vector is the third row times this vector. So the average fitness, we already had a formula for that. Well, that can be computed. Is P times AP. So P times AP. Well, AP is this vector here, which is 0.1 times 1.8 plus 0.4 times 2.4 plus 0.5 times 2.3, and then you get as average fitness this number. Well, you can compute the fitness of species 1. That's the first element of A times P, so this is 1.8. And you see that's higher than the average fitness, lower than the average fitness. So it is to be expected that the proportion of species 1 will decrease. And species 2 and 3 have fitness 2.4 and 2.3 respectively. So it is expected that those two species will grow. And species 2 will grow a bit faster than species 3. So we'll now move on to the definition, to the it's not a definition, it follows from other things, but we'll first give the continuous replicator itself without explaining it. Just give its intuitive reading, which is the change in the proportion of the species I at time t is equal to the size of the proportion of species I at time t times the difference in fitness and average fitness. So if it is fitter on the average, it will grow, and if it's less fitter than the average, it will shrink. That's the idea. And of course we have to multiply with the size of the proportion of species I itself, because, well, if the proportion is almost 1, then it must be, and if it grows, it must be nearer to 1. So it must be in proportion with the original proportion. So this is shorthand. Well, don't use that often, but it is official shorthand for the change of the proportion of species I in time. So it is just a derivative with respect to t of proportion I. Well, just to give a few examples, suppose a proportion of species 7 at a time point t is 0.2. So species 7, the presence of species 7 is 20%, and the fitness of species 7 at that time point is 6, and the average fitness at that time point is 9. Then the question is, what is the speed of growth for this species 7? Well, just apply the replicator equation, the continuous replicator equation. Fill out all the numbers, and you will see that because its fitness is smaller than the average fitness, species 7 will shrink with this amount. Or, sorry, will grow with this amount and will shrink with this amount. Other example, same question, same calculation. So the dynamics of the replicator can be quite unpredictable. So you see here, you start out with, so this is the previous example, and then the dynamics. So black is the magnitude of proportion 1, red is the magnitude of proportion 2, and blue is the magnitude of proportion 3. And you see that for some score matrices, the proportions do not converge in the replicated dynamic. Don't mind the second diagram. This is a phase diagram, but we have better phase diagrams, so just ignore that. So focus your attention on this graph here. So you see the proportions always add up to 1, and they vary wildly in time. Okay, next slide. So this is the same replicated dynamic we just observed. So the phase space, but this is the phase space in the simplex representation. And of course, the corners are always rest points of the replicated dynamic, because there only one species is present. So the advantage of this representation is that you can observe the dynamics for all starting representations, for all starting proportions. So here the starting proportions is that we have all species 1, and because there are no species 2 and 3, the dynamics will stay there, because the replicated dynamics will never introduce new species. That's a very fundamental property of the replicated dynamic, which we can prove, and which we will prove in due course in this lecture. So the circles indicate rest points of the replicated dynamic, and the circled rest points indicate Nash equilibria if the score matrix is interpreted as a symmetric game in normal form. So you see, not all rest points are Nash equilibria. So it is interesting to ask which rest points are Nash equilibria, because evidently not all rest points are Nash equilibria. I can already reveal that those rest points in which the replicated dynamic, well, here, stays in the neighborhood of that rest point, once it is in the neighborhood of that rest point, those are Nash equilibria. So if the dynamic is in the neighborhood of the rest point, once it is in the neighborhood of the rest point, it stays in the neighborhood of the rest point, then it's the Nash equilibrium. And here you can't see that, but it is the case. So you can't derive from the picture alone that this is a Nash equilibrium. So the open circles are computed with Gambit. So the whole picture is generated within NetLogo, but computing Nash equilibria is too complicated to implement yourself. So NetLogo calls Gambit to compute the Nash equilibria, and then draws the open circles here to indicate that these are Nash equilibria. Next slide. So of course you can have replicated dynamics in higher dimensions. You see here a replicated dynamic of 4 species, 1, 2, 3, 4, represented in the 3 simplex. So the simplex in 3 dimensions. Well, let's look at that for just some additional. So did you know that NetLogo has a 3D version? And I just took a specific replicated dynamic that it is an interesting payoff matrix. Where is it? Well, the payoff matrix should be represented somewhere. Yes, it's hard-coded here. So I just took one specific replicator equation because it shows interesting dynamics, and to show you this in 3D. So you see that, among other things, you see that depending on the starting proportions, the dynamics converges to different limit points. And as you can imagine, the dynamics in higher dimension is more complicated than the dynamics in 3 dimensions, so for the 2 simplex. So we now have one limit point here and one limit point here at 0, 1, 0, 00, and so on. And we can have limit cycles, and in higher dimensions we can even have chaotic behavior. So just to give an idea what's going on in higher dimensions. So we have 3 important concepts of where those dynamics converge to or is invariant. So this is actually a system of differential equations, which means those different equations generate trajectories. We just have seen them in space. So we have a vector of at each point of time we have a vector of proportions, and of course a vector of, well, differences in proportions, in speed of proportions. And well, if there is no movement at some point, we speak of a rest point, of a steady state, of a fixed point. Rest point, steady state, fixed point. There are many other terms. If a rest point is close to P, then it always is close to P. So if that happens, then we call it Lyapunov stable. So the official definition is, if for every neighborhood U of P, there is a other neighborhood U prime of P, usually smaller neighborhood, such that states in U remain within the larger neighborhood. So you have to probably pick a smaller neighborhood to guarantee that the trajectories remain within the larger neighborhood. So basically Lyapunov stable, or just stable, means if you're close to P, then you remain close to P. Don't confuse stability with, for example, rest point. So a rest point is something, or a steady state is something else than a stable point. So don't confuse the two. And then a stronger, even stronger form of stability is asymptotic stability. That is, if you are in the neighborhood of a point, then you will converge to that point. Then the replicated dynamic will converge to that point. So this terminology is not specific to replicated dynamic, because it's terminology from differential equations and dynamic systems theory, but then also apply to the replicated dynamic. So you have the weakest form is a rest point, and the rest point may not be a stable point, and a stable point may not be asymptotically stable point, but the converse, of course, is true. If there's convergence in the neighborhood of that point, then of course that's a very strong form of being close, always close. And if a point is Lyapunov stable, or just stable, then it is of course a rest point. I'm not sure whether this, well, being a rest point follows from this definition. Probably. Oh, well, yes, it does here, a rest point P. So by definition, Lyapunov stable implies rest point. Okay. So what's very important in understanding replicated dynamic is its relation with Nash equilibria. State is in a Nash equilibrium. Well, by definition, if every other distribution of proportions yields less, or yields no more profit than that proportion against itself. So this applies for a symmetric game. So it's symmetric. So this should, I think this should actually be a symmetric Nash equilibrium, because you speak about two the same proportions here. So this equation means that for all q, the alternative distribution of proportions yields no more utility than the original distribution of proportions regarding to fitness. If you write this in full, then Nash equilibrium means this. Now, if for all species their fitness is not strictly higher than the average fitness, then of course it must be that all species assume average fitness. Of course, this must be so. This is just a property of numbers. And if this is the case, then from the replicator equation it follows that we have a rest point. So we now immediately have that a Nash equilibrium is a rest point. And a specific type of rest point, a saturated rest point, by definition, by name. And it works also the other way around, of course, because it's by definition. So on the one hand, if you have a Nash equilibrium, you have a saturated rest point, that's by definition, but the other way around it works as well. If you have a saturated rest point, like so, yeah, so basically proving the equivalence between this one which embodies the concept of a saturated rest point, and this one which embodies the concept of a Nash equilibrium. So from Nash equilibrium to this one, you just take Q with all 0 and 1 Q1. Then you obtain equations of inequalities of this form. And the other way around, if you only have equalities of this form here, then of course no combination of those equalities can supersede the average fitness, because the Qi are smaller or equal to 1, smaller than 1 or equal to 1. So a combination of those cannot supersede the average fitness because of this. So I already argued that therefore a Nash equilibrium is a rest point by this type of reasoning. And if you have a fully mixed rest point, so every species participate, that's very important. So in your programming exercise you probably choose starting proportions for your replicated dynamic in which every species is of course represented. So no PI is 0. Every species is represented. And so if you then apply the replicated dynamic to that proportion and you have convergence, then you know for sure that you arrived at the Nash equilibrium. Why? Because a fully mixed rest point is a saturated rest point, because all species participate. So that's very important. If you start out with proportions in which all species are represented, and you have convergence, then you know for sure you arrived at the Nash equilibrium. You can also prove which we don't do now. In a moment I refer to the sources of these proofs, that you have a strict Nash equilibrium, then you have an asymptotically stable point. So all these implications, so if you have a limit point of the replicator dynamic, I already indicated you have a Nash equilibrium here. And there follow quite a number of implications and interdependencies, which are now rather confusing because you don't have the overview right now, but in the end of this presentation I give an overview in which you see the interconnections. So this one I think is the most important, and this one. So you have a limit point in the interior of the simplex, you know for sure, the limit point of the replicator dynamic, you know for sure this is a Nash equilibrium. It doesn't hold the other way around. So although all stable points are rest points, all stable points are Nash equilibria, not all Nash equilibria are stable points. And this is an example of a Nash equilibrium that's not stable. We see here better what's going on. So the trajectories are moving outwards and then moving inwards. So this is not stable, because if you're here you may be thrown outwards and then thrown backwards in. But still, Gambit, at least Gambit, tells us this is a Nash equilibrium of this particular replicator dynamics, of which we don't give the payoffs, only the behavior. Okay, so far part 1. I think it's otherwise the presentation becomes too long. So I hope to see you in the second part of the discussion on the replicator dynamic.